we're going to take a 24 centimeter piece and we're going to bend it. We're going to bend it at so that there's 10 centimeters in the middle and 7 on each end. As we fold it up, what kind of shape will we get? A trapezoid, yeah. And there's a number of ways to do this problem. I'm going to choose an approach that is natural to me. A little bit of frustration second hour for people. The concern was, what if I would never know how to do this on my own? And again, that's the measure of your readiness as a math person. That's just, sorry, you just hope that over time you collect more and more pieces of information that help you out. So don't feel bad. Lots of people got questions on problems like this. But you know, at some time you want to be able to think through ones like these kind of on your own as you become more of a mature master. So I'm going to cut this into 3 sections. I'm going to have 2 triangles, and I'm going to have that rectangle. Okay? Now, I know that this area, or I'm sorry, this length is 10. This length is 7. And this length is 7. I do know that this part right here is 10, but I don't know that length, do I? And I don't know this length. But the question is asking, at what angle should I fold? And so really, you kind of got 2 angles. I guess, you know, you could either say that's the angle that I'm going to fold, so the red one, or you could say the angle from the base. I don't know necessarily which one you want. It doesn't really matter. You know, if Bo is doing this and I say fold it, he can decide which one he's talking about. But for this problem in particular, let's just write an expression for area at this time. Area is equal to, and sometimes you think that people do this just for teaching so that students can follow along. No, this is how I would start the problem. I'd say area is equal to 2 times the area of the triangles plus the area of the rectangle. Well, real math people wouldn't actually do that. Yeah. That's how I would start. Everything I do here is how I would start the problem. The next thing that would occur to me is something in the problem. I don't have it up on the board. I need to put a variable. I'll use x eventually. I'll use a height eventually. Theta. Why? It's an angle. Very good. And in this picture, I'm going to put, you know, theta. That's going to represent theta. Why did I choose that to be theta, not this one or that one? Anybody know? Because it's part of a right triangle. If I can figure out this angle, I can figure out the blue and the red, can't I? So that's what I chose theta to be. All right? So there's the rhyme and reason. Well, I don't know this length. We'll call it x. And I don't know this length. I'll call it y. Yes, very good. X squared plus y squared is 7 squared. If only that did it for us. The fact is that the shape of the angle is what's going to change this. So I need some type of equation that doesn't involve x and y, but rather involves theta. So, oh, very, very good. You guys see. So let's write it like this. Area is equal to 2 times, what's the 1/2 times, here's the variables I got, x, y, plus 10 times y. So now we're going to take your guys' thoughts and we're going to use some trigonometry here. And namely, I'm going to say that the sine of theta is equal to something, and that the cosine of theta is equal to something. Sine of theta can be written as what? X over 7. And the cosine of theta is y over 7. Therefore, 7 cosine of theta is equal to y, and 7 sine of theta is equal to x. How's that? See my little trick? Now, I can take this area problem. Instead of x and y, I'll only have what for a variable? Theta. One single variable. Isn't that nice? So area, in terms of theta, is equal to 2 times 1/2, 1. X is 7 sine, and y is 7. So I'll have 49 sine of theta, cosine of theta. Clear how I got 49 sine of theta, cosine of theta. Plus 70 cosine of theta. So I haven't made boxes, but what box would we have arrived at? Yeah, the third box. This is our equation. This is our function. So if you want to solve where it has a maximum, you would take the derivative and set it equal to 0. So let's take the derivative. In order to take the derivative, what rule do you have to use? Product rule. So a prime of theta is equal to derivative of 49 cosine, or 49 sine, times cosine of theta. Then the derivative of cosine is negative sine, so I'd have minus 49 sine of theta times sine of theta minus 70 sine of theta. You okay with that? So these are going to be sine and cosine squared, right? We got a problem. Does anybody see it? We want to solve this equal to 0. Okay, other than that. We can't have cosine and sine in the same problem in this situation. It just doesn't work to solve it. We got to use a substitution. Emerald, loud and proud, confident. You got a lot of good mathematics happening in your brain. Share with the rest of the world. Come on. Yep, that's what I want to use. So therefore, cosine squared of theta is equal to 1 minus sine squared of theta. That way I can get rid of my cosines and only deal with my sines. This goes there. There's your chance to look like a genius, Emerald. Sorry. 0 equals what? 49. 49 sine squared. 49 sine squared. Awesome. Negative what? Negative 98 sine squared. Ooh, how do you solve that? Ooh. No, totally illegal. Marcus is referencing the very commonly used negative 49 product property. Doesn't work. Saying has to be set equal to 0. Have to keep it equal to 0. Okay? Sine inverse, no. This has quadratic form, does it not? I mean, everybody, if this was negative 98x squared minus 70x plus 49, what would you do? Yeah, you're darn right you'd put in the quadratic formula. Do it. Instead of solving for x, we're solving for sine of theta. That's what x is in this problem. So you tell me, what do you get when you do negative 98, negative 70, and 49? Draw it out further, 0.43. Okay, and then the other one. Okay, first of all, can sine ever be equal to positive, something bigger than positive 1 or less than negative 1? This is absurdity. So, second of all, where is sine positive? Which quadrants? First and second. Thank you very much. So we have sine equal to 0.435 in those two quadrants. So that'll be my reference angle that I'll use when I get a reference angle. But the question is, look at your original problem. This theta value, can it be greater than 90? No, you're not going to fold it more than 90. So do we need to worry about this one? No. So let's just get the first one. They solve for sine of theta equals 0.435. Sine inverse. Do you think the carpenters are going to work in degrees or radians? They're going to work in degrees. I've never seen. You ask somebody for a 90-degree square. Can I have the pi over 2 square? All right. So, math thing. All right. Shut up, Luke. All right. Thank you, Sine. All right. 26 point what? Oh, 25.87? 88? Gosh, give me a number. 25.79 degrees. Awesome. Yes, thank you. So we've got theta. Let's answer the problem. This theta right there is 25.79. And thank you, Miss Katie, for doing that. Others were being lazy. So sine inverse was 0.435. Sine inverse of 0.435, 0. And you got to make sure you're working in degrees, not radians, because carpenters don't work in radians. Yep. Sure, I'd be very, very productive. Okay, so there we go. So the question is, what would the blue angle be, folks? Add 90. And if you add 90, you get 115.79 degrees. How do we get the red angle? And if we did that, we would get 64.21 degrees. Done. Get to your sign when we get back. Shortest one ever. Okay, so on your assignment, your what? Well, you have 2 homework assignments from this section, okay? So first of all, you had a worksheet, problems 1 through 6. 6 was optional. 5 is challenging, just to warn you. But from section 4.7, page 284, I'm looking for you to do problem number 11, problem 22, '44, 46, and 56, and 61 is extra credit. Yes. Now, I want you to know a few things. Number one, 61 is a problem from pre-calculus last year. You remember the hovercraft problem? So now you apply a calculus idea to it, so it's very similar to that. Okay, it's written by the same author, Stewart, so he takes some calculus pieces and moves them forward. Second of all, 56 is the gutter problem. 46 is the largest slope problem, which we did yesterday. 44 is cut a triangle in a quadrant problem, which we did yesterday. 22 is a parabola, or a rectangle in a parabola. I'm sorry, rectangle in a parabola problem, which we've done, right? 11 is just a little different. A little different, okay? So if you can't get 11, please move on to the others. I want you to know that for every 5 problems I give you, 4 of them are generally ones that you've done already. I just try to give you one that requires that aha moment, that setup of, okay, how would I accomplish this? Which is like number 5. And sometimes people say, well, I can't just come up with that. Welcome to my world, okay? Where when you take graduate level courses, half of the problems that you get in the course require the aha moment for proofs, and sometimes you don't get them, and you're just like, shoot, that's the way it is. So you got to be able to wrestle with it and think about it and work towards a setup. So there you go. Got it? Any questions? Okay. Shout out to Taylor. Anybody?
Sup, Twillis. Hi.
Matt Carlson purposely does not want to say hi to you.
Today, Mr. Gens looks like Gogurt.
Willis, we have the court trial on Monday. You better be studying.
Taylor, I'm just thankful that when you miss school, math is probably the number one class you think about, so that you can go find the video. Brings me joy that you're hearing my voice somewhere outside the classroom right now. So later.